I'm Laurent Lemmens and I'm a last year PhD student in the Ghent Quantum Chemistry Group. I would like to thank the organizers for providing me with the possibility to share our group's vision on research in computational sciences. I will be dividing this talk in two parts. The second part of this talk will be about sustainable development, but I'd like to start with a discussion on reproducible research. Let's take a look at a paper that was recently published. So, some calculations were done with a well-established software package, and they were verified with an in-house code. And then some other calculations were done with the in-house code. I think that the way research is done in this paper is pretty problematic, because nowhere do we find in the article a reference to the in-house code. So there's no way for me to reproduce this research. Then let's take another example. A new computational method was developed in the developer's version of some other software package. And now let's take a look at the most recent overview of documentation of this package. We can't find the implementation in the relatively recent release. This isn't necessarily a problem. I'm okay with software dropping features, but previous versions are a pain to compile, and that's a problem. Our research group has also suffered some problems. On the left, we see the very first graph that was generated in one of our new research lines in 2017. But the thing is, the PhD student left, and so did the possibility of reproducing the data. His code only compiled on his laptop and was, I'm sorry to say, a total mess. So in order to re-tackle this problem, we had to spend a significant amount of time on re-implementing the routines from scratch and making sure that we could compile it anywhere. And so here's the example of 2019, where one of our recent PhD students tried to reproduce this data. Unfortunately, he abandoned his PhD course, and we suffered from the same problem again, how to reproduce this data. So the previous examples mainly focused on the software, but what about provisioning and the actual data points instead of just a graphical representation? What about which compiler was used and which flags and which options were used for the compiler? And what was the hardware on which the calculations were performed? Part of the scientific method is that research should be reproducible. And in many other disciplines, we find an experimental section in articles that clearly outlines the steps to take in order to redo an experiment. So how can we make computational sciences reproducible, at least for quantum chemistry? We have to be radically open and focus on three parts. We have open software, we have open infrastructure, and we have open data. And of course, DSLs, domain-specific languages, can help in all three categories, but more on DSLs in other parts of this conference and in the second part of this talk. We can start by versioning the production code, for example on GitHub, and then every commit can be linked to a DevOps pipeline. And if basic quality checks pass, like the code actually compiles and the unit tests all pass, a next step would be to deliver a Docker container. And through the Docker container, the code will run on any platform that has Docker installed, so we don't have to worry about compiling and installing the right dependencies with the correct compiler flags and in the right folder, etc., etc. Docker really makes our lives easier. And we, at least as quantum chemists, also have to start working like real data scientists. We should all start working in Jupyter notebooks and really embrace the flexibility of Python as a data manipulating language. And then bonus points for versioning the Jupyter notebooks themselves, making sure that how the data is reproduced is up to date. And we can even extend our provisioning workflow by using Singularity, which is Docker for HPCs, so we can target our builds on larger computer systems if our research requires it. Remember the old graphs? So here's how we do it now. We have a Docker container that is related to our current code library. We have a Jupyter notebook that one of our junior PhD students wrote, which is also versioned on GitHub. And then we spin up a Jupyter notebook from the Ghent University HPC and let it crunch some numbers for us, and we can finally fully reproduce the data that was first calculated in 2017. It took us over 3 years to do it, right? But we are finally here. As I've said, one of the paradigms that we can use for targeting open computational science is through the development of DSLs, domain-specific languages. First, let's take a look at what sustainable actually means. It means making sure that what we have done doesn't go to waste. It's not about just keeping in existence. There's also an aspect of competence, making sure that what we have done, we keep our efforts in good shape. So how do we keep our coding efforts in existence? We should focus on concepts and interfaces rather than an ever-growing set of new computational methods. In this way, even if the underlying architecture changes, for example, by switching to a quantum computer instead of a classical computer, the high-level concepts don't need any modification. We would then just need a way to adapt the high-level concepts to the hardware. But the main reusable concepts, they remain in place. So why do we need DSLs? And what's the link between The Mandalorian and the Unreal Engine 4? Unreal Engine provides video game artists with a way to quickly render game scenes, to control projectiles, etc. But as an artist, you don't necessarily care how all this is implemented in a low-level computer language. You just care how you can intuitively create a landscape or a character or a set of video assets. Now, the graphical artists from The Mandalorian actually used Unreal Engine in the production of The Mandalorian. So in this analogy, Unreal Engine is the domain-specific language, and the video artists from The Mandalorian are its end users. In a way, how we should think about this problem is comparable, at least by analogy, to the internet stack, where each layer provides services to the next layer. And if we think about it, we'll have a couple of distinguishes we will have to make in the roles of the development of our computational technologies. We have the computer experimentalist, which is using a software package to calculate or predict properties of a new material, or he's trying to analyze real experimental data with computed data. And then there's the computational method developer, who is providing the tools for the experimentalist to use. But also there's the DSL developer, whose job is to provide software components, reusable objects, and interfaces that can be reused among many kinds of method developers. So we think about the DSL designer providing services to the method developer, who is, in his or her turn, providing services to the computational experimentalist. In quantum chemistry, I'd say almost all code developers are only focusing on providing tools for the computational experimentalists. And as far as I know, we're all reinventing the wheel, and we're not focusing on sharing common building blocks. In the past couple of slides, I've given a small overview on why DSLs are important and what kind of problem they target to solve. So what are we doing in our research group, the Ghent Quantum Chemistry Group? We think that traditional quantum chemical software hasn't been focusing on these intermediate or high-level objects. So we are, as I've said, just reinventing the wheel over and over again. Think about how much time this is costing for our community. Now, in our research group, we don't focus on implementing all new possible computational methods. We focus on establishing the common building blocks for those. And since we have focused on these building blocks, we can tackle the actual method developing, which is the second layer of the development stack, pretty flexibly, which is the kind of workflow that we need if we want to do rapid prototyping of new computational methods. And in the remainder of this talk, I will highlight two ways that demonstrate this flexibility. As a first example of the flexibility, I would like to address how we deal with basis transformations. Basis transformations are a concept from linear algebra in which we transform the matrix representation of various kinds of operators when we transform the underlying basis of the corresponding vector space. We require transformations of different kinds of objects, and by focusing on the mathematical objects that exist in the theory, the corresponding software library will feel natural and intuitive to use. For example, in theory, we have different kinds of orbital bases. We have general, unrestricted, and restricted spinor bases. And what we did in the code was implementing a one-to-one correspondence between the theory and the objects. So, as in theory, we have general, unrestricted, and restricted spinor bases available in the code. But it doesn't stop with just orbital bases. We also have basis transformations themselves that we have represented in several different objects. We also have condensed wave function information in 1 and 2 electron density matrices. And we also have 1 and 2 electron operators that exist in theory that are represented in our code. So let's compare how our code handles basis transformations versus how a well-established package does it. the well-established package, is PySCF. Even for an experienced developer, the code in blue is pretty hard to read. After spending a couple of moments deciphering it, I could recognize that this code performs a basis transformation of a certain 2-electron operator. And then afterwards, in green, it anti-symmetrizes its elements. Now, let's take a look at how GQCP does it. The 2-electron operator G is defined beforehand, and we apply a transformation T to it. And afterwards, we anti-symmetrize it. As a method developer, being in the second level of the development stack, I would rather use the .transform API instead of 10 lines of code that I would probably be horrified of every time I looked at them. Another way that we target development flexibility is by focusing on flexible algorithm design. Almost all computational methods use some kind of iterative scheme in order to solve a set of equations. So in order to improve on the flexibility of these methods, we have to be able to intervene in these iterative cycles. This flexibility isn't about opening up some set of heuristic parameters. No, I will be talking about real structure-modifying changes. How do we design a modification to an algorithm? Often we would just copy an implementation file of the first base algorithm and then just manually add the extra modification steps. Of course, this isn't a very sustainable way of working, because for a compiled language, we would have to recompile the program every time a small modification is made. So there has to be a better way. Let's think about algorithms in the following way. By decoupling the algorithmic steps from the environment, calculation space, set of intermediates, we can actually view an algorithm as a list of steps, where every step can read and write from the environment, updating the most current values for intermediate variables. Now that we have established algorithms as lists of steps, adding more steps at runtime has become pretty easy. We can define custom functions in Python that can interact with the environment and insert these modifying steps in the appropriate place of the base algorithm. So this was all conceptual. Now let's take a look at how we have used this in practice. Here's how a specific kind of quantum chemical solver is implemented in our software package GQCP. This kind of solver is the base solver for the example I will be discussing, and it's implemented, as you can see, in C++. We've implemented every step separately, and then we have added them into the iterative cycle. One of our bachelor's theses used the kind of flexibility that this approach offers. At least they defined a custom Python function in a Jupyter notebook that modifies one of the intermediates. And afterwards, we just insert it into the base algorithm at the correct position. So this talk has been an overview of how we are solving problems in our research group. I've talked about what some current problems are in the reproducibility of quantum chemical data, and what steps we can take in order to be more open in our computational research. And I've also talked about some considerations about domain-specific languages, and I've discussed two examples of how our DSL for molecular electronic structure has helped research in our group. I'm really interested to know what this community thinks. Thank you.
Hello, Roland.
Hi.
Thank you for the talk. Very concise. There are some questions in the chat, and we have a little bit of time, 7 minutes or so.
Okay.
I have also some backup ones here in our cheat sheet, so to say. Now,
Okay.
first, maybe the question from Agathe Jouet. She was referring to the Jupyter notebooks, which you also mentioned here at the end again. So she was wondering on a general note how Jupyter notebooks can help you in the striving for this reproducibility of research, and also that in conjunction with the pipelines which could be using containers. So maybe you could shortly elaborate a little bit more on that point.
Yeah, okay. So I think the difference is in the which things you're providing. In the case where you're using the pipelines, I think you're actually in more of an experimentalist trying to like gather data. For the Jupyter notebooks, that's something that we are trying to use in order to develop new methods, new algorithms, and new other stuff. So we need the flexibility to make changes at runtime. So we have to make some small adjustments or do something, I don't know, crazy in order to test some new method if it works and if it doesn't. And then afterwards, you can of course set up a pipeline that uses the methods. Of course, yes. But it's the level of application that you're using. That's the main difference, I think.
Okay. I mean, in our business, bioinformatics, life sciences, we also have this combination of, as you have seen before, I think, also in the talk from Björn, in fact, where you need like heavy computing eventually using Galaxy or other tools in a workflow, and then, as you said, the smaller bits and pieces where you need high flexibility, which then people either use Jupyter Notebook or RStudio or something like this, where you have more interactivity, but still you want to have a reproducible way of doing. And then, since you can share the notebooks, it's a kind of easy way to do that. Have the two things in the same time.
Yeah.
Good. Thank you for that illustration and the additional points on it. So one question from Thibault, in fact, who says, you were talking about the DSL developer and the software developer, and I mean different flavors or roles developers could take in. So how do you see this combination of people who develop methods and people who develop the domain-specific languages? How does that work out? Do they have to be in the same team? Can they be far remote, etc., etc.? So how is it working in your area?
Okay, I really like the question because that's actually how I think so our software package came into existence, because we wanted to do like some new methods, but we didn't really find any like package that could be used like Psi4 or PyCF, like big packages that we could modify easily in order to implement what we wanted to do. So we had to take a step back and think about what are the concepts that are important, inspired on theory. So we had to make it. We had to make the DSL in order to accommodate our feature requests. So we didn't know it at the time, but now we do. And again, that's how research is done at the moment in our group. So there's a new concept that we're trying out in theory. So we work it out in theory, and then we try to use our library. And if we if we see that we are misusing objects or using them in a way that they weren't prepared for, then we're taking a step back and thinking of, oh, can we generalize these ideas in order to accommodate even more features? So that's how our language was born. Yeah.
Okay, very good. Maybe one general question, since you mentioned how we work, and of course it's always nice to see others pick up your own work. So we were wondering, or those people who have prepared some questions on how is your now I have to read the abbreviation GQCP.
Yeah.
How is it used already beyond the groups or at Ghent, or do you see any uptake anywhere else?
Yeah, we so we had a postdoc that was a part of our group for a couple of years. Now he has tenure in Canada, and now he's also using the package. But more than that, I'm sad, not yet. That's why we're trying to I don't know, do some small networking in order to make contact with other method developers, so that we can gain some experience on how they would use it or
it's always
it.
indeed an important aspect. So
Yes.
especially building communities, it's also kind of a tedious job sometimes. So
Yeah.
I do second your situation, or let's say second your argument, because it's indeed not simple. Yeah. Good. So hopefully that works out in the future as well.
I hope
and
so.
Another question, we still have one maybe, which is on more technical, or maybe technical and the distinction between what you have created in GQCP with respect to library and DSL. So where does the DSL start, and where is it just a functional library?
Okay, that's a good question. I'm afraid I don't really know the answer because I was only introduced to the concept of DSLs like 2 months ago or something.
Okay.
I didn't really know that was what I was doing or what we were doing in the group. And then I was introduced to the concept. So, okay, maybe it's a function library or an I don't know, software development kit or a DSL. I'm not sure what the real distinctions between these things are. But I think the most important thing is indeed the correct levels of abstractions. Yeah.
Okay,
indeed.
very good. Good, thank you again, Laurent. You will be still around, I think, if people have questions in the chat or eventually in the networking session. So again, thank you also from my side.